We are close to wrapping up the lessons in the second semester of physics for first year engineering, and this lesson is about the properties of waves. It will be an overview of the following two lessons where we'll talk about the details such as speed, velocity, tension in strings, and so forth. So the learning outcomes for this lesson are to be able to point to examples of waves in nature and around you, to describe the various kinds of waves, pulses, so single peak versus periodic waves that repeat, traveling versus standing waves, and transverse versus longitudinal waves. We'll see how to mathematically describe the properties of waves in space and time, and we'll be able to determine them then. So wavelength, period, frequency, and speed of waves. If you're thinking of a wave, the first thing that may come to mind is this fantastic picture of a surfer, say in this case, sliding down a giant wave. Looks amazing. In fact, waves are around us every day, everywhere. Light is all around us, and light is an electromagnetic wave. And light covers a whole range of wavelengths, from X-ray to radio, or frequencies, if you think of it in a different way. And the visible part of light is just a small range of this overall spectrum of light. So you can see here, to shorter wavelengths we have ultraviolet, even shorter is X-ray, shortest still gamma rays, longer is infrared, none of those are visible to the eye, microwaves like what our microwave oven produces, radio waves at longest wavelengths. Light and then sound, another clearly important sense. Sound is actually a combination of two kinds of waves. We have a waves on a string, which is a transverse standing wave, as we'll see. And there's also waves that are produced inside the belly of the guitar, and these are actually longitudinal waves. They're pressure waves, which is actually what is producing the sound that we hear well. So waves are linked to simple harmonic motion. We have studied the behavior of a single oscillator, but if we consider an extended medium like the ocean or like air, then what happens at one place affects what happens right next to it. So oscillations at one point will drive oscillations in the neighboring points. And so this will then lead to a wave that will propagate through the medium. And waves can, as a result, be thought of simple harmonic motion that is happening at many points simultaneously that are connected with each other. And let's take a look at some examples of waves. Here's a traveling wave pulse. So we pull on a string once, and it sends a pulse through the string with certain velocity in the right direction here. And we will see that what is guiding the speed of the pulse is a tension in the rope, and it's a difference in the tension between the one end here and the other end that actually drives whether the rope goes up or down. So you can see, for example, the angles here with the horizontal are slightly different. So a pulse, or this is a solitary wave, it's a single propagation. By the way, you notice right away here that the rope itself does not move left and right. It's only the pulse that moves to the right here. So there's no matter being moved to the right along the rope here. There's only energy being moved to the right along the rope here. Only the propagation of the pulse. So waves on a rope or on a string are called transverse waves. So they'll move energy along the motion of the propagation. Transverse waves will the string itself will be moving perpendicular to the duration of propagation. So that's what definition of a transverse wave is. And you can see you have definition of wavelength here, which is a distance between two neighboring peaks. So again, a transverse wave is where the medium in which the wave propagates oscillates perpendicular to the direction of propagation, transverse wave. You can also have a longitudinal wave where now the medium oscillates in the direction of propagation, but again, only back and forth over a small distance. And here's an example of a longitudinal wave. It's a wave that's created on a spring that you push back and forth. So you have regions of compressed string here and regions of where the string is stretched here. So as your motion is back and forth, you're creating these longitudinal waves on the string. So this is a periodic because it repeats, traveling because there's energy being transferred from one end to the other, longitudinal wave. And here's another example, a periodic standing transverse wave. It's transverse again because there's motion up and down. It's standing because there's actually no, as we'll see, there's no net propagation of displacement one way or the other. And it is periodic because this oscillation actually repeats. This is what we have, for example, on the string of a musical instrument. And let's go back to our ocean wave. This is an example of a traveling transverse wave pulse. So if we just consider one of these waves, it's a single wave pulse. Of course, if you consider many waves in sequence in the ocean, then you have a periodic wave. So let's see how to describe mathematically waves. As we are already familiar with the equation from simple harmonic motion, we can use we can write an expression in terms of a sine function, or a cosine in this case. We have an amplitude, we have an angular frequency omega, which is shows you the time dependence, but we also have a spatial displacement now. So we have this number k in front of the spatial coordinate, and k is called the wave number, and it's 2 pi divided by the wavelength, or alternatively the wavelength is 2 pi divided by the wave number. So this is an example of our wave. This is the wavelength, so this is displacement in the y direction, and this is distance in the x direction. So this is our wavelength, and at time 0, in this case, we can see that the disturbance, the wave, peaks at time 0 and then peaks again a full wavelength later. This particular wave has no phase to it, so we could have an extra phase term after here, which here is set to 0, which is why the wave peaks at time 0. Now, a short time later, if time increases, this wave that was initially here will have appeared to have moved slightly to the right. So in this case, time here is pi over 4 seconds. So this is t1, here is pi over 4 seconds. So then the phase of this wave has changed. And as time continues to increase, then the phase will continue to increase, and the pattern will appear to propagate along the string. This is an example of a traveling wave. And here, because we have a negative sign in front of time, this wave actually is propagating in the positive x direction. And we'll see how to create waves in the negative x direction as well. So here's an animation of what the motion of this wave looks like as time evolves. Again, this is distance along the string, and this is the transverse displacement. Now, if instead of distance we actually plot time here, we get a similar looking graph, where now this is, if we're standing at the origin of the string at x equals 0, then our expression for the wave is just a cosine omega t. And then we'll see that again, after one now period, as opposed to wavelength, the vertical displacement returns to where it was initially. So this is how we define the period of a wave. And again, note here that on the x-axis, I do not have displacement along spatial direction, I have time in this case. And the period is going to be 2 pi over the angular frequency, omega. And each point along this string now oscillates as a simple harmonic motion. So this is a wave that is traveling in the positive x direction. I mentioned that we could also create waves traveling in the negative x direction, and that's done by simply changing the sign in front of time. So now this is an example of a wave that's propagating to the negative x direction. So again, compare. The only difference here is the sign. This is a wave traveling in a negative x direction. This is a wave traveling in the positive x direction. So let's take a look at some of the basic properties of waves. We talked about the period, t here, and the distance lambda that's covered during one period, and this is the wavelength. And then we can relate the wave speed then as lambda over t, the wavelength over the period, or this is f, the frequency, times lambda, or omega over k, the angular frequency over the wave number. So k is 2 pi over lambda, the wave number, and omega is 2 pi f, omega being the angular frequency. So then we can actually write our expression for the wave, for the displacement in the vertical direction. This was the expression that we originally had. We can actually just express it as k times x minus vt because of these relations here. So this is a different kind of general expression for a propagating wave. So let's put these expressions into an example. We have ripples in a puddle that propagate at a speed of 34 centimeters per second. So this is our wave speed. If the wave frequency is also known, 5.2 hertz, find 1 the period and 2 the wavelength. So very simple stuff. The period is 1 over the frequency, so 1 over 5.2 hertz, hertz being second to the minus first power. So this is a 0.19 second. This is 1 period of a wave, and then the wavelength is the velocity times the period, or otherwise the velocity over the frequency. And putting in the numbers, we have the wavelength is 6.5 centimeters. So we talked that this, in fact, is the general expression for a wave. X, it's any sort of function of x minus velocity times time. And let's assume that y peaks at time when x minus vt equals to 0. Then as time will increase, we saw that the location of the peak will change. And this, again, wave having a negative sign in front of time, this wave moves to the right. And the peak will always occur when x minus vt equals to 0. This was our initial condition. So in fact, we'll see that the x location of the peak will propagate with time as v times t. And now, so we see that the x location of the peak will increase as time increases. So that's why this wave is propagating to the right. That's how this minus sign gives us a right propagating wave. And to generalize this, any expression of this form will give us a wave propagating to the right, whereas any expression of this form, where there's a positive sign in front of the time, will give us a wave propagating to the left with a speed v. And again, important point here, we're showing the oscillation of a string. The string moves up and down, but it does not move back and forth in this here. We have a transverse wave, and even if it were longitudinal waves, the oscillations would still be very small and be confined to a region. They would not actually be moving along with the wave. Think of it as having an element of water, or a bucket water here on the surface of a lake for which we have waves propagating. What is happening to this bucket of water is that rather than actually, if it's actually well embedded in the surface of the water as opposed to just surfing on top of the waves, what happens is this water, as the wave comes around, actually does a circular motion. So this is, I call it a bucket of water, but it's actually a cork. So it actually stays in one place, more or less. It's confined to this location. And similarly, in a small volume of water around this cork moves only a small amount as opposed to moving along with the wave. Let's take another more detailed example. We have 4 different traveling waves, and they're described by these equations in A, B, C, and D. So they're all different slightly. They have different amplitudes, different wave numbers, different angular frequencies. And we have a few questions here to analyze these waves. Which ones are moving to the right? Which ones are to the left? Which ones have the same period or same frequency, if you will? And what are the speeds of each wave? So let's go through this for each of these questions. We already saw that the direction of the wave is dependent on the sign in front of the time parameter. So negative signs in front of time give us waves moving in the positive x direction. So A and D are waves moving to the right, whereas positive signs in front of the time argument give us a negative propagation in the negative x direction. So B and C are moving to the left. Which ones have the same period? So the period is 1 over frequency. It's also related then to the angular frequency. And this factor here is what gives us the angular frequency, the one in front of time. So this was our expression for the wave. It's a cosine of kx minus omega t. So this is the angular frequency in front of the time. And the period is 2 pi over omega. So if we find the waves that have the same values of omega, we find the waves that have the same periods. And so we see that waves A and C have omega of 21 radians per second, and waves B and D have angular frequencies of 42 radians per second. So these two pairs have identical periods. And finally, what are the speeds? So now we just should look at the ratio of the angular frequency over the wave number, because that's what speed was. So then the first one has 21 over 3, 7 meters per second. And then the second one is 42 over 6. And that's moving now to the left, so minus 7 meters per second, and so forth. And this is the end of our lesson on overview of the properties of waves.